Oh, hello, 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 everybody. I'd ask everyone take your seats. Thank you, thank you. Far too kind. But I'm not the person that we're celebrating today. So good morning, all. My name is Christopher Etienne, and I am the program coordinator and kind of a community liaison for our graduates who participated in RVU and ASAP internships. This year's program pushed our scholars out of their comfort zone and challenged them to engage in various fields of research in STEM and research in the humanities as well. And these include research in sociology and public policy, quantum mechanics, fluid mechanics, mechanical metamaterials, and molecular phase dynamics. So I got to give a hand for that. I really didn't know some of these things existed, until our interns started participating in it, and a lot of our interns were participating in these programs. For the first time, they were interacting with STEM and research on such a high level, and I want to say, and I just want to like kind of convey some of the thoughts that your mentors had regarding your ability to like navigate these programs, and everybody was astounded by just how far you've been able to come in such a short time. So it's my honor today to just to take some time out and kind of just appreciate your accomplishments and give you the flowers that you deserve. But I wanted to say that despite the rigor of your caseloads, you are able to learn coding, hone your research and computer literacy skills, and exceed the expectations of our mentors. I am honored, and I have been honored to be here with you as you navigated through your internships, and look forward to your continued accomplishments as you navigate through your academic journeys. With that said, I thought it would only be right for us to actually bring one of our intern alums, which was part of, I think, one of the first cohorts of RVU internships, and give him an opportunity to speak a little bit about his experience, and also highlight, how he's been able to help our students, our interns, navigate through their internships this summer as well. So, Damien.
Good morning.
Morning.
It's a beautiful thing to just be in this space. Congratulating my brothers that have completed something that is going to take you to other levels in your careers. I got an opportunity myself in 2017 to be on the campus working with Jill to write a grant for the NSF. And the second year, I got a chance to go to the Czech Republic and build a cluster and travel Europe a little bit. And this internship takes you to levels and places that you never think after being incarcerated you'd be able to go. I became a licensed social worker. So I got my bachelor's and my master's at Rutgers and started doing a lot of different therapies and trying to figure out how we support each other. And when given the opportunity to come back and just sit in the room and work with our brothers and sisters, because we had some sisters last year, and just talk about what you're dealing with, what you're going through, and be able to say, all right, I've been here before. I know what that feels like. It's not something that you should suppress, talk about it. And we just had open dialogue every single week. And then we would just sit down and talk. We'd go to the mall and talk. And that's really the support that I was able to bring and I'm able to give to my brothers and my sisters that are coming home. Because when you come on this campus, one of the first things I say is, don't forget you belong here. You put in the work, you know where you want to go. And no matter what anybody says, tells you, the way they look at you, always remind yourself that you belong here. You're not an imposter. So I just want to congratulate them, and I wanted to let y'all know exactly what I do, how we do it, because these 5 gentlemen are going to do great things. And when they get an opportunity to put this on their resume and go out, people are going to accept the fact that they are the best of the best. So thank you for being here and continue to support this program.
Okay. Hello, my name's Ali Muslim. I'm one of the REU computational biology interns. Today, I want to start off by imagining there's a wall in between us. And in that wall, there's holes. Now, we can see one another. But what if I tell you when I'm talking, you will not be able to hear me? That is possible with phonetic crystals and the shape of how the holes are. Phononic crystals are materials that can control sound waves through Bragg scattering. Bragg scattering is the way waves interact with regular repeating patterns of atoms in a material. The waves bounces off and they create a distinct pattern of scattered waves. Now, phononic crystals can be made of hard material or soft material. As you can see right here on the left, this is made of iron. And on the right, this is a soft material of phononic crystals. Why does this matter? Today's discussion is about different shapes and holes. The shapes and holes that make up of phononic crystals due to compression to determine whether sound get by or not. Studying phononic crystals is important for various reasons, as they have significant applications in both scientific research and also technological development such as acoustic engineering. Acoustic engineering is a branch that deals with sounds and vibrations. By tailoring the periodicity and geometry of the phononic crystal, engineers can create materials with specific acoustic properties, which can lead to development of sound installation, vibration control, and noise reduction. Within this area, it can help industries like construction, aerospace, and electronics. But before we get to this part, we must start from the beginning process. This photo illustrates how the shape and changes are due to compression. Over the summer, I looked at how phononic crystals deform when the shape and the holes changes. Video ain't going. Well, the video is not going. What this video would have showed was a compression on the y-axis, whereas though the crystal would have been compressing like this here, and it would show interlocking patterns. Here we go right here, thanks. As you can see, as the phononic crystals compress, they go into an interlocking pattern. As I go on, I will show you slides that will explain this in further detail. The process that I needed to analyze these shapes was a three-step process. The first process was to create a mesh. Now the mesh is lines and points that you make on a graph and run it through Phoenix. After running it through Phoenix, which is used to solve equations on a mesh, you run it through the ParaView, which you can see on the slides. This is the mesh. You run it through Phoenix, and then this is the structural image that it comes out to be. Phoenix is a computer software, and also ParaView is a computer software. Right here you have circles of phononic crystals of a radius of 0.35. On the left side, you have 10% compression. On the right side, you have 20% compression. As you can see, uniaxial X and uniaxial Y, the circles by the naked eye still look the same as no compression right here in the middle. When you compress uniaxial, it's compressed like this on the X level. And when you compress it on the Y-axis, it's compressed like this. As you can see up top, when it's compressed equal biaxial, Y and X, this is the interlocking pattern that I was explaining to you when you seen it on the machine. As you look at 20 compressions, all three all have the same interlocking pattern, but the shapes are different, but the patterns are the same. After doing this here, I decided to increase the radius, which you can see that all 6 pictures all have the interlocking pattern, whether it's uniaxial or whether it's equal biaxial. After noticing that these are the same, I changed the shape and used squares. Now in the squares, you will notice that uniaxial X and Y, whether it's 10% or whether it's 20%, they do not have the interlocking pattern. But when you compress both equal biaxial X and Y, they have the same interlocking patterns. When you increase it, it still has the interlocking pattern. Now what I observed from this here is that when you compress equal biaxially, the X and the Y, you always come into an interlocking pattern. The knowledge that you can learn from this can go on to do future work that can extend to other holes, shapes, to find general patterns in poster formation, connect generalized patterns in symmetry, properties, or phononic crystals, find properties of sound waves traveling through compressed phononic crystals, and the one that I saved for last, although it's up top, is understanding shapes and phononic crystals may lead to understanding the structural colors by controlling the shapes of photonic structures. And the reason why I saved this one for last is because photonic structures deals with light. So therefore, if you can understand the shapes of phononic crystals and manipulate sound, there may be a possible way to understand the photonic crystals, because shapes also dictates the same way shape dictates in phononic crystals. So you could probably understand how to control structural colors. Finally, the acknowledgments. I cannot give all the titles because I only have 10 minutes. So I'm gonna just read off the names. Jill Stockwell, Dr. Bridget Von Holt, Christopher Etienne, Tara and Rhonda, Dr. Ophelia Mensah, Sarat, I cannot pronounce your last name. Sorry about that. For Amanda Quirk, Jenny Green, Somali, Majuda, Taish Reddick, Dr. Tamara Nelson, Mike Key, Princeton University, New Jersey STEP, and my REU interns, Paul Boyd, Wally Palmer, and Claude McDougall. Hope you enjoyed this presentation and hope you enjoy the rest of the presentations that follow. Thank you. That thing wouldn't crush mine.
I do have a mic we could shop around if there were questions from the.
Okay, thank you. That was a really great question. My name is Marion. I'm one of the new instructional specialists at PTI. I really appreciated your presentation, and I was wondering about some of your results. You showed some really interesting things where, like, when you have the circle and you do the uniaxial deformation, you can get to a point where you get that cool interlocking pattern, but that never happens with the square shape. And I'm wondering, yeah, if you have any kind of ideas why, you know, what's special about a circle shape versus the square shape, where, you know, given enough squishing, you do get that interlocking pattern, but that never ever happens for the square. I guess I'm wondering if you have any idea.
At this time, I have no ideas for it, but I just noticed that when you do it equal biaxially, as I said that wrong, equal biaxially, you have the interlocking. So this is just further studies that need to be done to try to figure out why the squares don't have that. And also when the last slide where I showed future work, this one, as you can see right here on the left, these is images of all different kinds of shapes. So the ideal is to try many different shapes to see, is this a pattern? No, when you do it equal biaxially, will you still get that interlocking shape? And if you do, then maybe you can answer that question. Why do some of them, when you do it unibiaxially, it doesn't do that, but when you do it together, it always do that. So that's something to study further on.
Yeah. Very good. Thank you so much.
You're welcome.
Well, good morning, ladies and gentlemen. Obviously, my name is Paul Boyd, not Boyled. But I want to thank you all for joining me, and I'm grateful for the opportunity to address you all today. The topic of my presentation, you can read it. So the yin and yang is a familiar symbol that we may have all come across at one point or another. And for those who are not familiar with this symbol, let me provide you with a brief meaning. The yin yang symbol is captivating because it represents the idea of being in Taoist belief. Keep that in mind. Being refers to our conscious experience as living beings beyond just what we perceive as real. According to Taoist philosophy, being has two fundamental aspects: order and chaos. This makes sense because in every situation, there are things we can predict and understand, as well as unexpected elements that can surprise us. Another fascinating element about this symbol is the black side with a small white dot and the white side with a tiny black dot. And let me fix this real quick. There we go. This symbolizes that chaos can change into order, leading to significant transformations. Conversely, even within orderly and predictable situations, sudden events can propel individuals into chaos. Therefore, despite appearing to be opposing forces, they engage in a perpetual and dynamic interplay. In the yin yang symbol, the two halves complement each other, forming a harmonious whole. In parallel, RNA binding proteins have a specific regions or domains that complementarily bind to RNA molecules. These interactions are crucial for the proper functioning of RNA binding proteins, as they enable the proteins to recognize and bind to specific RNA sequences or structures. Moreover, RNA binding proteins play a crucial role in balancing different RNA levels in the cell, promoting stability or degradation based on their function, maintaining cellular homeostasis, and proper gene expression. This analogy highlights the significance of complementary interactions for the proper functioning of RNA binding proteins. Additionally, RNA binding proteins play a multifaceted role in regulating intrinsically disordered region proteins. Their interactions with IDPs can impact RNA metabolism, protein function, and cellular processes, making them key players in the dynamic and intricate network of cellular regulation. In the realm of IDPs, there exists a dynamic equilibrium between ordered and disordered states, akin to the fluid interaction of the yin and yang. IDPs continuously oscillate between structured regions and disordered segments, folding into defined structures during interactions or adapting to cellular tasks through conformational changes, exemplifying inherent dynamic balance. Unlike structured proteins with well-defined functions, IDPs serve as regulatory elements, interacting with structured proteins as flexible and adaptable partners, much like yin and yin complements yang's stable nature. Despite their ambiguous functionality, IDPs play vital roles in cell signaling, transcriptional regulation, and other processes. IDPs form intricate cellular interactions, engaging in multiple protein-protein interactions and participating in complex regulatory networks. IDPs influence various cellular pathways, much like the interconnected halves of the yin and yang symbol. Moreover, IDPs are crucial drivers and regulators of phase separation in cells. Their ability to undergo weak multivalent interactions and form dynamic assemblies allows them to influence the formation and function of membraneless organelles, impacting the cellular processes. In liquid-liquid phase separation, biomolecules segregate into two distinct liquid phases, mirroring the symbol's two halves. These separated liquid phases exhibit different properties and functions, creating a balanced system. LLPS involves a dynamic balance with biomolecules continuously exchanging between the phases based on cellular conditions, reflecting the fluidity and balance of the symbol. These phase-separated biomolecules can form membraneless organelles and structures, fostering specific cellular processes through interconnected biomolecular networks, much like the symbol's interwoven halves. In the cell, LLPS brings functional balance by organizing and compartmentalizing cellular components, enabling efficient regulation and coordination of biochemical reactions. Moreover, LLPS sensitivity to environmental factors like temperature, pH, and biomolecular concentrations reflect its adaptive nature, paralleling the symbol's responsiveness to change in environment. Lastly, phase separation is a fundamental process that underlies the formation of the formation and regulation of biomolecular condensates. Just as the symbols halves complement each other, biomolecular condensates form through complementary molecular interactions, bringing together diverse biomolecules into organized liquid phases. These condensates constantly exchange biomolecules with the cellular environment, and the equilibrium between the two phases is crucial for their function and stability. Furthermore, biomolecular condensates, I should say, exhibit sensitivity to cellular cues and environmental changes, rapidly assembling and disassembling in response to their signals. This adaptability mirrors the yin-yang symbol's adaptive nature, enabling cells to respond and adjust to different conditions effectively. However, abnormal biomolecular condensates can have far-reaching effects on cellular processes and functions, contributing to the development and progression of various diseases. The yin-yang symbol's complementary halves find a parallel in the functional duality of intrinsically disordered regions within RNA-binding proteins. Mutations in IDRs can upset protein function, leading to more structured conformations that reduce RNA interactions or enhance disorder, affecting binding affinity. In RNA-binding proteins, IDRs work harmoniously with structured domains and precisely, regulate RNA interactions. Mutations can disrupt this harmony, causing dysregulated RNA binding, impaired cellular processes, and disturbances in cellular homeostasis. The effect of mutations in IDRs depend on their context. Consequences may vary based on the specific RNA binding proteins, RNA targets, and cellular environment, emphasizing the importance of considering the broader context of mutation effects. Specifically, mutations in the RNA binding regions of the protein can impact its interactions with RNA sequences, and structures, affecting phase separation behavior and influencing the composition, stability, and functionality of biomolecular condensates. These mutations have dynamic effects on disease pathogenesis, with disease phenotypes potentially manifesting differently over time or in response to cellular conditions, making disease progression unpredictable and complex. Proper phase separation is vital for cellular organization and function. Mutations that impair normal LLPS can lead to dysregulated cellular processes, contributing to disease onset or progression. For example, the yin-yang symbol's complementary halves find a parallel in the structure and function of TDP43's low-complexity domain. Mutations in the low-complexity domain disrupt the equilibrium between structured and disordered regions, affecting TDP43's normal LLPS, interactions with other cellular components, and cellular behavior. This imbalance contributes to the pathogenesis of neurodegenerative diseases, where abnormal TDP43 collection is a common feature. The yin-yang symbol's balance between opposites reflects the functional balance required for normal TDP43 function. Mutation in the low complexity domain can disrupt this balance, leading to aberrant phase separation behavior, pathological aggregate formation, and impaired RNA regulation. These disruptions contribute to the neurodegenerative diseases like ALS and frontal temporal lobe dementia, where TDP43's misregulation is implicated. So, what are some ways we can tip the scales towards balancing the degrading effects of neurodegenerative diseases? While experiments provide valuable structural data, molecular modeling offers insights into dynamic behavior and energetics that are difficult to observe experimentally, leading to a more comprehensive understanding of complex biomolecules. Molecular modeling enables the simulation of biomolecules' motion and interaction over time, essential for comprehending diseases like FTLD, where abnormal dynamics and interactions play a role. By exploring intricate interconnections within biomolecular systems, such as protein-protein and protein-ligand interactions, molecular modeling reveals the underlying causes of diseases and potential therapeutic targets for FTLD. Additionally, molecular modeling contributes to the understanding disease mechanisms, including protein aggregation, structural changes, and interactions with cellular components, crucial for identifying targets and designing therapies to restore functional balances disrupted in diseases. In drug discovery, molecular modeling offers a flexible and adaptable platform for screening and designing potential drug candidates targeting specific biomolecular components involved in FTLD, accelerating the drug discovery process and increasing the chances of finding effective targets. So, I embarked on a preliminary investigation employing molecular dynamic simulations to explore the effects of mutations on IDR, on it, which is intrinsically disordered region, of TDP43. The underlying purpose was to attain profound wisdom concerning the intricate interplay of these mutations on the protein structure and behavior. By unraveling this delicate balance between function and disease within biological systems, we hope to unveil the essence of harmony that governs their existence. The yin-yang symbol highlights the most constant aspects of being, the enduring truths. Some may question their reality, but they are indeed very real as they stand the test of time. In life, there are always things we can grasp and things we cannot, and they all contribute to our experience of being alive. Thank you.
Anyone?
That means I did a good job.
Who would like to?
Thank you so much. That was so exciting. So I know nothing about science.
Same here.
Get the philosophy and the metaphor of the yin yang. So I'm wondering, hearing your peer fellows speak about what you brought with philosophy to science.
Mm.
How do you see moving forward? What is the science bringing to your understanding of philosophy?
Well, in the reverse, I saw, based on my lab, this is my lab right here, y'all, these fine people right here. Can you believe it? Every last one of them showed up for me. So that speaks for itself. But anyway, I can use them as an example to answer your question. You know, each one of these people, Murat, Nate, Paul B, he's Paul number 2. Obviously, Jarrell Joseph, Nicole, Alina, and Ananya, they all specialize in something different. And then as they come together, they're not forming a whole of the whole, right? But they're part of the whole. So, you know, Murat, I kind of see as he's a cagal body, right? And Nate, he is a rigid body, right? And Jarrell is the nucleus. And Paul B, he's what should we make him, Nicole? He's a stressor, yeah. But anyway, you know, they all work together in unison, and their goal is the same. You know, they all, you know, put their little parts into it, but their little parts add up to something that's going to do something good in the future. You know, they might not, none of us may live to see the results of this, right? But the interesting thing is that we're willing to, this is an example, a great example of, you know, putting your biases aside and what you think you know, and you put that aside to come together to formulate something to get to know, right? And that is the great thing right there. You know, the getting to know process is what it's all about. And that's what's special. And then not only is it special, it's a great thing because of the inclusivity part. You know, look at the diversity in there. You know, there's a lot of diversity in there, and you need diversity in order to move these things forward. And that's why we're all sitting here right now, right? So there you go.
Thank you, Professor. How's everybody doing? My name is Waleed Palmer. Ecstatic and happy to be here. These past 9 weeks has been wonderful. One heck of a journey. I'm here to talk to you about my research efforts involving quantum cascades lasers, designing and optimizing an actionable laser. These lasers play a pivotal role in the advancement of technology because of their extremely and unique characteristic. These lasers have a wide range of applications. Biomedical. Their biomedical use includes non-invasive diagnostics and imaging because of their tunable mid-infrared wavelengths that can penetrate biological tissue. This includes breath analysis also that can monitor glucose levels, cancer detection, and even all sorts of abnormalities in the body that can be easily detectable with these particular lasers with accuracy and efficacy. Gas trace sensing. These lasers are widely used in gas trace sensing applications, especially for detecting gases and pollutants in the environment. Defense and security. Through the detection of chemical agents, explosives, and surveillance systems, these lasers are well suited for infrared countermeasure intelligence. Thermal imaging. Their high power output enables them to enhance image resolution and sensitivity in night vision and infrared microscopy. But this merely just cracks the surface of what these lasers can do. Now, my particular efforts involve designing my own particular laser this summer. Quantum cascade lasers basically are based on the principles of inter-subband transition of quantized states within a multiple quantum well heterostructure. Now, what does this mean? Well, inter-subband transition of quantized states just simply refers to the act of an electron transferring from one energy state to another within the same conduction band. Now, if you look here in this particular area, here, this is what you consider to be a conduction band. Hold on, I can't see this. This is way too small for me. Who got this small like this? I gotta change this. This one right here is too small.
Yep, there's a vertical line.
Hit max. Where is that?
No, you don't.
I'm a PC guy. Okay. Well, as I was saying, this area here, this is your conduction band, right? Now, as you can see here, this green arrow here, this is an electron. The electron has to pass through this injector region right here, and then it makes a vertical transition down into what is considered the active region. This red arrow is also electron, but when it passes through the active region, it shoots off a photon, which is light. Now, this process, it takes place as many times as you can repeat the process as whatever you set it to. But how this laser transitions through the injector and the active region is where the whole idea of cascading comes from. That's where you get the title quantum cascade lasers. Now, as I said before, these lasers are based on inter-subband transitions of quantized states within a multiple quantum well heterostructure. Well, the heterostructure refers to the interface between two different types of material compositions within the quantum well. Now, okay, now we're going to the next slide. Again with the Mac. There we go. Okay. All right. Now, you'll see here, this is basically a depiction of the software that is used to basically design and simulate quantum cascade lasers. Now, you have here your materials. This is considered your barrier materials because it consists of indium and gallium and arsenide. And this here you have is considered your well layers. here, which is consist of aluminum, gallium, and arsenide. Now, the difference in these two materials plays a big factor in how the design of the laser is going to interact. These here are your layers. On this particular conduction band, you have 22 layers. This is layer 1, which is your barrier layer, and this is your last layer, which is your well layer, from 1 to 22, and it repeats. The process repeats in this particular conduction band 4 times. As you see here, is set to repeat at 4. Here you have your energy field. Your energy field just basically determines the amount of electric conductivity that you want to display. Then you have your dipole, your low scattering, and your figure of marriage. All of these come down to the figure of marriage. Being able to design an effective laser all semis down to getting a great figure of marriage. Because when you have a great figure of marriage, then that tells you that you have an optimizing laser. Now, in my first model to find an actionable laser, I generated a sequence of layers based on an educated guess using the technology centered around Irvin Jr.'s tutorial. I realized that in doing that, such measures were not great. After I started studying particular literature and started extending my research, I realized that the approach I used, it made no sense at all. As you can see here, my energy states are all over the place. These little squiggly things, these are considered your energy states. There was no quantized separation between the energy states, and there was no way for me to identify a particular active region, which is usually in this area, or an ejector region. And as you can see here, my figure of marriage is at 45 picoseconds square angstroms, which is relatively low for this particular model. So when I selected these 2 states here, this is the results of the calculations that the software Irvin Jr. gives you. Now, when I decided to come up with my second model, what I did was I read a bunch of literature by my faculty mentor, and I started seeing a particular pattern in how these lasers were designed using sequences within the wells and how the thicknesses of the material compositions were used. And I just came up with a system of layers that made more sense. I constructed the layers in sequential orders and descending orders, and I set my well layers. Here is particularly what they consider to be your quantum well layers. I made sure those layers were thicker than the rest of the layers. These are the active regions. These are the injector regions, where they're relatively smaller, and I did that purposely. And you can see from this particular design that up here, you have what is considered like population inversion, which is just simply when a system exists. In this case, the system is a state of energy that is taking place up in the higher region, as opposed to in the lower region is more higher than the lower. But you can see here that you have your electron transitioning here, and it's shooting off a photon. This is considered, the active region, as I said before. But as compared to my last laser that I did, none of that activity is taking place. And you can see the difference between the two. Not only that, my figure of marriage increased by particularly a lot, 540 picoseconds squared angstroms. So it got a whole lot better. But I wasn't satisfied with those results, so I decided to take my experiment even further. And with Model 3, I got even better results by increasing some of the barriers and decreasing some of the layers, the well layers, and decreasing my energy field by 60 kilovolts per centimeters to 54 kilovolts. I was able to come up with a whole lot better figure of merits, 1600 to be exact, picoseconds per square angstroms. That is a very well laser. And you can see the transition here. Even though it's more diagonal and it's not vertical, the transition is excellent because your figure of merits tells you this. This leads me to wonder whether the electrons will have to work harder in making that transition. But here, as you look at this right here, this calculation right here, which is your tau upper, is significantly higher than your tau lower. That means these energy states up here are significantly higher than these right here, and that's what you want. You want those to be relatively higher because it encourages this electron to make that intersubband transition. So my next model was even better. Even though my figure of merits increased only by 60 picoseconds angstrom squared, it still was significantly better by me just increasing some more barriers and decreasing some more layers and decreasing my energy field selection of these two energy states. I got a better figure of merits. But I couldn't stop there. I just kept going with it. And then in my fifth and last model, my figure of merits increased significantly, I would say, to 2,536 picoseconds angstroms. Now, I did that because what I did was I increased each layer by 5 angstroms. Angstroms is just basically the measurement of about 100 millionth of a centimeter, because we're talking about subatomic particles that you can't see with the naked eye. They're very small. And I reduced each layer I reduced layer 2 by 8 angstroms and reduced a couple other layers, and I gradually increased layer 10 by 10 angstroms. And I also took off 2 layers to spread out the composition of my materials. And here I got the greatest result that I could possibly think to get in this particular situation. And so I would say that with that, I came up with a way greater laser. And so if you look at the model summary of each model, my figure of merits increased significantly with each trial. But here you have the dipole. Now the dipole also decreases, which I didn't necessarily agree with, because your dipole is where if you have a smaller dipole, it could disrupt the laser activity. But in this case, my figure of merits was so high, it didn't really matter, because what that tells me, my upper tau, now that was so great in each model that I know that all my energy states within the upper part of the transition was so great that it was going to give light irregardless. And so I can say that in this whole process of me doing this and constructing these particular lasers and these designs, that I was able to come up with something that was rather actionable, something that can be probably used in all types of industrial use throughout the world. As I said before, in gas trace sensing, breath analysis, where they can just put a tube in your mouth and detect all sorts of abnormalities and things of that sort. And so in my work, this is what I particularly did. I used the software Irvin Jr. for modeling my own QC and designed a high performing laser to maximize it to the highest possible figure of merits that I can come up with. The initial Model 1 was not a good laser, as you've seen before. It had a very low figure of merits, but my last model was very excellent. It had a high figure of merits. And if given the time, I would take Model 2 and build on it in a manner that would decrease my dipole while increasing my figure of merits. Well, that's it for me. I just want to take this time to acknowledge the people that played a big fundamental role in this whole process of this summer internship. The director of this program, Ms. Bridget. Thank you very much, my brilliant faculty mentor. Thank you for being supportive and helping me out. Jill Scott, I said Jill Scott. Jill Stockwell. Sorry about that. Surratt, my boy Surratt. He's been very supportive in helping us get through this process. My day-to-day mentor, Andres, who's not here right now. Flo has been very supportive in conducting everything. And Chris has been very good at putting things together. Galen, who's not here also, he has been a good, excellent teacher at providing us computational skills. Amanda Quirk, who's also not here, she was one of the first instructors that help us through physics type teaching. And Caroline, the data analyst, very, very good instructor. And Sonali, also, who's not here, was very instrumental. All these people were very instrumental in making this process what it is. And I'd like to thank all of y'all. Thank you. That's
Thank you, Shahara. I appreciate that. And just to kind of give a little background so that it makes some sense in terms of what my role in the research process has been. I've learned that my background was to study business and law. And in studying business and law, patents, trademarks, and intellectual properties was an area of interest for me. So having an opportunity to observe how that part of the process comes into play from the beginning of this whole research cycle, I realized right at the beginning that we had roughly 900 research students here at the university this summer. And out of the and we had an entire research village. And in the various areas that we were operating in, starting with, for example, my particular area was the computational biology area. I realized that the study in these areas is very, very broad. As you've heard research coming from a number of different areas, and it doesn't stop there. It's a massive undertaking in terms of research. So I wanted to understand a little more how the research process takes place. And usually, as in most things, there's a cycle, there's a life cycle. And that life cycle tends to start with funding and it kind of ends with funding. And so I wanted to address that. And my slide here in particular just kind of addresses, if you notice the colorful structure, that's actually a scanning of the carbon fibers the aerogel carbon fiber systems that they've studied throughout the entire process. There's a unique pathway with carbon, and if you remember, some of you are old enough to remember the old carbon paper that used to be inside of your documents. You used to pull it out, and you would sometimes get it on your hands, and it would be all over your hands and fingers, and then they got a little more sophisticated with it, and it ended up getting integrated into one sheet to another. And so as those sheets wrote, they took the paper out, but the carbon was always an interesting substance. And so coming to this stage here, I realized that right away we were going to be dealing in an area that I thought would be quite interesting, because I learned very quickly that the Arnold group that I was a part of was dealing in these carbon fibers, these and aerogels that had been derived from things as simple as egg whites, and taking egg white proteins and then turning these into carbon by baking them at very, very high temperatures. And you're going to see here in just a moment some of those processes that took place. But there's been some amazing research that's come out of this. But this research cycle, I wanted to first off address as you see it here. The research cycle right at the top starts with solving problems. What is the issue? What is the problem? How can we solve a problem? Once we move beyond that process and develop this problem solving, which has been taking place, each and every one of the speakers who've come up before me have been talking about a various area of discipline that they're working in, but they're problem solvers. And so as they move through this problem solving technology, they come up with inventions. And these inventions that are being developed at some point will turn into some level of an item that needs protection. It's an intellectual property at some point. And that property that becomes what we see on the end of the spectrum usually needs disclosures along the way. At some point along the way, we have to figure out how do you not let this technology get away from you, and you can continuously making improvements for society. How can you, how their benefactors are obviously that's going to need that. In our case, we were working with the ability to take desalinated water and well, desalination of the water through a filtration process and allowing that desalination process to come out with clean drinking water, removing the particles out of this water. And so we move to the disclosure phase. The next phase we move into is the assessment of these products. So before they hits the market, there's an assessment process that needs to take place. Is it something that's already been done? Is it a product that had that at some point may be at a stage that we need to do additional research before we take it to the marketplace, before we take it and try and find someone to invest in this product at that level? And if that is the case, then what kind of protections can we place or put in place before these products are released or before these inventions are released? Some of the inventions are, and we've had some that are, quite amazing, as you'll find out. Here's some very recently. As a matter of fact, there was one patent that had just been released here at Princeton over the last year that was quite noteworthy. It was dealing during the medical phase. I'm sorry, the the pandemic phase. Yes, I'm sorry, the pandemic. And during the pandemic, and so it was research that was done right here at Princeton that was a part of that. And so when that type of technology is coming to the market, again, it has to be something that's going to allow that to take place. So we move from there to the marketing of the products, the startups, or if you choose to start up, some of these will spin off into individuals owning their products and wanting to be involved with the development of it as it goes into the industry. Others may decide that they want to continue to do the work in the lab and they want to turn it over to an industry and allow that to continue to expand from there, giving it to an existing company. It then moves into a phase of licensing, consequently into commercialization, and then into revenue that is starting to be generated, and that revenue is quickly reinvested back into the universities and back into the research that was developed. Now, this particular slide here just kind of speaks to all of the various amounts of research that takes place, but at the end of the process, there's usually a single idea that turns into that one light bulb, that one piece of research that ultimately turns out to being the one that needs that entire process. Now, much of the funding comes from this particular organization that's deeply involved with the funding processes. So the grants that are written, the National Science Foundation has been around since 1950s, and they work very closely with universities. They've developed an entire department where much of the research that needs to happen, they understand that they have a three-phase process that they approach it with. One is the promoting of the progress of science. Another is the advancement of the national health and prosperity and welfare. And then the third area is national security. So many of the things that you see that take place here, these plasma machineries, I've went to some plants, the facilities that actually are involved in much of the development of many of these plasma technologies right now, and fossil technologies, and it's just an amazing thing to see as you go along with it. But this particular little slide here was one that I found to be pretty interesting because it just addressed the lightweight aerogel that turns the elements that make up this aerogel are so fascinating that it's delicate. The flower that you see that's sitting on top of that is delicate enough to allow that Bunsen burner underneath it to burn and not destroy the flower. Well, the research that's going on in the carbon gel, as you can see there, is pretty broad. Our research, of course, dealt with the ability to desalinate water through the carbon fiber. But we also have found that the research goes on in the areas of thermal installations, aerospace and aviation, oil spill cleanups, protective clothing and gear, building materials, energy storage, soundproofing, environmental remediation, lightweight compositions, which is one of the more areas that we're kind of, that touches the areas that we're dealing in, and medical applications, cryogenics, and transparent insulations, just to name a few. And there are actually even more than that that they're involved in. So the research is broad, the areas are broad, and we're not limited to just one particular area. And I kind of enjoyed the idea of seeing the broad research that's involved with patents. Patenting this kind of technology. Let me see, I may have opened it. Won't change. There we go. Okay. So in this particular slide here, what we're addressing is the economic viability. So in order for this process, one, we know that the inventions that are being developed are inventions that are noteworthy. It's worth promoting science. It's continuously being involved with national security. So with that being the case, here in the economic viability area, these are just some of the areas that they focus on through the National Science Foundation targets in terms of being able to provide their funding. Now, this organization in last year alone put in $9.54 billion in research. And so university research is a major focal point for what they do. And the grants and the resources and the funds that continue to come into it are pouring into it because of the type of work that's coming out of it. But what you see here are just a variety of the areas that they're placing that research into. And the biological sciences, the computer information, engineering, of course, social behaviors and economic sciences. And there's just, it's a vast, broad variety of areas that they're focused on, and the funding that's needed in order to continue this research is going to be placed. Now, this just kind of touches briefly on the area in which I was having some exposure to. In the group with Dr. Arnold, what we were dealing with was the ability to take this particular substance that we're all familiar with, and it's just an egg white. The egg white that you see on the left was turned into what eventually the arrow is pointing to, which was the aerogel that was allowed to capture about 98.2% of the ionic impurities inside of this water. That water and the specks that you see in there graphically is the impurities that's actually inside of this water. Now, by taking this egg white and taking it through a process of moving it into the freeze dried, it's first freeze dried, and then the freeze dried component is then moved into the cooking of the freeze dried product, egg white protein, and then it's turned into a carbon. And this carbon is what you're looking at, or a form of a carbon for this illustration. And what we do is at that point is that they then begin to slice into this carbon, opening it up, and then there are all kinds of of interconnecting fibers that the carbon produces that allows for this filtration to take place. And in that process, the resulting at the end of it, at the very bottom here, you can see is fresh water. Now, this process that's been currently been developed right now results in 99.9% of the nano and microplastics contaminants being removed from the water, which I thought was just fascinating. It's drinkable water. You can only imagine what this type of technology would be when moved into the marketplace. And if, of course, someone has taken time to develop it, and the amount of research that goes into doing this type of study obviously has to be protected. This speaks a little bit more to that particular product, that invention that's actually taken place. You see where they are, the proteins in the egg whites are then freeze dried, and then it moves over into the next phase as it's cooked at the 900 degrees Celsius. And that particular baking process in these special ovens that are used is what is allowing that to happen. And so that indication here, I think it's a number B, from what I can tell here, is number B is where you're seeing they're actually cutting into that, and the separation of that is what you're looking at below. When you're seeing the illustrations where the little red lines, if you can see that, is actually showing you just what it actually looks like if these fibers are laid in very thin sheets. And the thin sheets are put together, and this is what's the water's passing through. Now, once that process is complete, this is here, the Bayh-Dole Act of 1980 is what has been, for the most part, created to allow the protection of these patents. And working directly with the universities. This application and the disclosures that you see there is what that's addressing. The patents is actually one of Dr. Arnold's patents that was done earlier, and the applications and disclosures are what was done in terms of how that process took place before it became a patent. We have it here at Princeton, and there's an office of trade and licensing that actually is called OTL, and they actually work very closely with the professors, the postdoc students, in order to be able to ensure that their research is protected, and that the research is allowed to flourish in the industry as it moves to the next phases of being marketed into the industry. Now, what we're talking about here is licensing and agreements. Ownership. Do you lose everything once you get involved in the process of developing a product? And the answer to that is no. Does the university have the ability to have a stake, become a stakeholder? Are they involved with that process of the product that's been developed? And then, yes, they do, and they are allowed to do that. And that's what the Bayh-Dole, legislation was about, allowing that to actually take place, where universities could be involved in owning and having an ownership stake in these types of technology. And the benefits, of course, can come back to you. There are ways that you, as an inventor of this kind of technology, and the reason that takes place, needless to say, is that the equipment alone, I was looking at the cost involved, for example, in some of the scanning equipment. It ranged anywhere from about $50,000, I think it was the leased in on for used technology, up to about $1 million, just for these, just for the technology itself that's used to do the scanning and some of the work that's involved. So when you're really involved with this type of research, it's a very costly process, and that's why universities are heavily funded through the United States government. Once that process is completed, you see here where it shows you where the startup or licensing. If you decide that you want to spin off into a startup, you can do that. If you decide that you want to move that product to some of the larger companies, like in the pandemic era, where they decided to take the developments and move it over to companies that already had distribution, then this is kind of an example of that and what that can look like. Whether it's you as a small mom and pop shop, and you want to take it and continue to work with it, or you may want to turn it over to a larger industry and allow them to move forward through licensing processes. And that's what the office here of technology and licensing will help you and assist in that process. And that's, again, is where the revenue comes back. As these things are done and as this research is established, you're able to now take that research, allow that research to become a means of generating additional resources that are now reinvested back with the universities, back to the inventors who have there's processes where they can share in the financial rewards of that kind of development. And this is where the cycle begins all over again. It starts all over again. So it's a 30,000 square foot view of just what actually happens. But I think the research, at the end of the day, when you want to know why so much is being focused on research, this is why, because it is a cornerstone of the university process. And I just wanted to pass that out. So hopefully that makes sense to you. All right.
Good afternoon, everyone.
Good afternoon.
My name is Afia Ofori-Mensah, and I am Director of Equitable Postgraduate Academic Opportunity in the Emma Bloomberg Center for Access and Opportunity, which is Princeton University's center focusing on the needs of first-generation college students, low-income students, and others historically excluded or marginalized within higher education. An initiative of the Emma Bloomberg Center for Access and Opportunity is the Aspiring Scholars and Professionals Program. This is an internship program that we began 2 years ago in partnership with the Prison Teaching Initiative that was designed to introduce students from a variety of backgrounds to the possibility of taking on careers in higher education by pairing them with Princeton faculty and staff members in order to conduct research or do professional internships in the summer, and then encouraging them to continue on with undergraduate research or professional internships on their home campuses during the academic year.
In my research, my eyes were open, so to speak, because I was enlightened not only on the prevalence, causes, and consequences of housing insecurity, but also the core drivers of poverty that so many low-income families, particularly people of color, are faced with here in America. For example, 4 in 10 low-income people in New Jersey are homeless or pay over half their income for rent. And more than 300,000 people in New Jersey households use federal rental assistance. Rental assistance is significant because studies show that people who experience housing insecurity may likely face eviction. And eviction has been linked to homelessness. And homelessness, in turn, can lead to a host of problems that impact our society. Now, let me just tell you, I too experienced housing insecurity, eviction, and homelessness. And trust me, it ain't nothing nice when you're out in the streets with no home to call your own. There ain't nothing nice when you've seen and experienced eviction and homelessness, and when you are forced to relocate under those circumstances. At times, it was so painful that I literally cried. I did not like the fact that either myself, a family member, or a friend had been forced out of a dwelling place we called home because we could not afford to pay the rent any longer. Some people falter under those circumstances and experience mental health and wellness issues, alcohol and drug abuse problems, and some even resort to crime. And as we all may know, crime leads to incarceration. And to be candid with you all, I could tell you that I, myself, experienced all the above. Oh, but let me tell you, I've come to learn of a place we call the Eviction Lab. For example, throughout the summer, people have often asked me, what is the Eviction Lab? What do you guys do in the Eviction Lab? So let me start by answering the former first. The Eviction Lab is a research center located in the sociology department at Princeton University. It was founded in 2017 by Matthew Desmond. He's a sociology professor here in Princeton. The lab is the first organization to have created a national estimate of evictions. This is significant because the federal government does not track any information on evictions. Consequently, the Eviction Lab's mission is to document the prevalence, causes, and consequences of eviction here in America. Thus, lab personnel conduct research, collect data to help inform policymakers, advocates, tenants, and the general public about evictions. Understanding evictions is very important too, because it raises awareness of housing insecurity and homelessness. For example, people of color, particularly Black renters, account for 20% of the nation's renters, but they receive over 30% of all eviction judgments. In 2018, there were 3.6 million evictions filed in the United States, while women are at a higher risk of eviction than men. And families with children are 3 times as likely to be evicted. The most frequent evictions, however, they occur in the most disadvantaged urban areas, specifically those areas that suffer from high crime rates. Now, during my internship, there were some specific needs expressed to me by the Eviction Lab staff. Since the inception of the Eviction Lab, its research has focused primarily on evictions. However, the lab has recently expanded its research to look more broadly at housing and economic inequality. One of the ways that they're doing this is by researching the amount of government benefits that go to homeowners versus renters, which is something I've come learn to know more about in my research project. In addition, my research included, but not limited to, researching controlling laws and policies regarding federal subsidies, Section 8 programs, vouchers, state and local taxes, and low-income housing tax credits. And so, at this time, I feel that it's important for me to explain some of these terms. Let us begin with Section 8 rental assistance. This program is known as Section 8 because it is outlined under the 8th section of the United States Housing Act. The Section 8 program is actually 2 separate initiatives specified under the Amended Housing Act of 1937. The program formally began in the United States in 1974 with the creation of the Housing and Community Development Act. Next, we have Housing Choice Voucher. Through Section 8, low-income tenants receive financial assistance by way of Housing Choice Vouchers. A voucher is a piece of paper or a document that entitles a holder to a discount or that may be exchanged for goods or services. These vouchers allow recipients to obtain affordable housing. Finally, for this presentation, we have federal and state subsidies. A housing choice voucher can be a federal subsidy. It could be benefits given to an individual, business, or institution, usually by the government. They can be direct, such as cash payments, or indirect, such as tax breaks. Subsidies are typically given to remove some type of burden and is often considered to be in the overall interest of the public. So there you have it. Those are some of the key terms I've come to learn during my research project, based solely on the needs that were expressed to me by Eviction Lab staff. Speaking of staff, as you all have already met her, Catherine Dole and Carl Gershenson were my supervising mentors. Lauren Traum and Tasneem Yusufali were also instrumental in my research project. They all provided me with the necessary technological equipment, stationery, and information to facilitate my work, which I began to perform by researching Rutgers Library database under Westlaw and various organizations and government websites such as urban.org, newjersey.gov, and huduser.gov, among others. As a result of my research, I've come to learn that there is much more information needed to help policymakers, advocates, tenants, and the general public about evictions, including the time it generally takes to receive a housing voucher. I've also come to learn that more federal dollars go to home ownership subsidies, which mainly benefit higher income households instead of those families that are struggling the most to sustain housing. Mm. To me, these matters are of central importance because many low-income families, particularly people of color, are struggling to make ends meet. And some are being deprived of the minimal civilized measures of life's necessities. To be blunt, they are poverty-driven and poverty-ridden. It is clear from these facts that I'm giving. New Jersey communities, among others in this country, can only thrive and abide when everyone, renters and homeowners, black, white, brown, yellow, you name it, we claim it, but all should have access to decent, affordable housing. Now, just as I myself can relate well to the issues of housing insecurity, eviction, homelessness, and yes, poverty too, my research project in the Eviction Lab is the first phase of an ongoing research study, which has allowed me to get a greater understanding of housing and economic inequality here in America. And sources such as NewJersey.gov, Tax Policy Center, and Center on Budget and Policy Priorities, among others, provided me with a great deal of relevant information. However, I did indeed struggle a bit to locate some data, had a little issues here and there. Consequently, I consulted with my supervising mentors, some Princeton librarians, other cohorts, and staff members here at Princeton. They were all readily available to guide, instruct, and answer my questions, which allowed me to overcome those research hurdles and move forward with the Eviction Lab's mission of collecting data and documenting the causes and causes of eviction here in America. Despite all the painstaking work that is done here in the Eviction Lab, much more research and funding is needed to provide awareness and solutions to this national crisis of housing and economic inequality. The Eviction Lab's research has also shown that economic inequality and evictions are not only a consequence of poverty, but also a cause of poverty. Thus, I implore you all to look into the eviction crisis here in America. And while it may or may not be an issue to you, it certainly is a fundamental issue that so many low-income families are struggling to overcome. And that, my friends, is a major problem for society as a whole. As I mentioned earlier, housing insecurity can lead to eviction. Evictions have been linked to homelessness. And homelessness in turn can lead to a host of problems, such as mental health and wellness issues, drug and alcohol abuse, and crime, which has a bearing on incarceration rates, increased incarceration rates. With that said, I would like to thank you all for this opportunity, your time, and your attention. I would like to go to my acknowledgments here, and I would like to thank the inspiring scholars and professionals of Emma Bloomberg Center for Access and Opportunity at Princeton for this amazing opportunity and experience. I would like to thank New Jersey Scholarships and Transformative Educations in Prisons, Rutgers University, Raritan Valley Community College for granting me the opportunity to earn a higher education. I would like to also thank Dr. Afia Afora Menza. You all have met her this morning. I would like to thank Catherine Dole. You all have met her this morning. I would like to thank Carl Gershenson, Lauren Traum, Shavari Tachachar, Annalon LeMay, Tasneem Yusufali, Nick Grace, Peter Hepburn, and Sarat Tungusari or Kundusari. Which one is it?
Tankasuri.
Tankasuri. Well, thank you. May take me a minute, Sarat, but Mr. Sarat here was very instrumental. I would like you all to know in helping me, along with my supervising mentor and Dr. Afia Afori. They were very helpful to me with all of the research and all of the needs that I readily had to have at my disposal. And let me tell you, Sarat is an amazing guy. I've learned a lot from him. I learned that we grew up in some of the same areas, I say, so to speak. And I've learned a lot from my supervising mentor. They provided me with a lot of, I'm challenged so much with technology, how technology has evolved. And so they were so amazing in my life. They were so amazing because they brought me to a different point in my life now. And I feel better about navigating, even when I get on the computer today. And so Dr. Afia, oh boy, we had so many career workshops. And I mean, the knowledge was just flowing off the top of her head. She provided us, among many other students, with outstanding help and academic growth. So I would like to thank you all and so much. And also, finally, I would like to thank my cohorts from the program here. And I'm going to start with Chris. We had community group meetings every week, and Chris was on point. Chris said, "What, man, what you doing late?" If I walked in 1 minute, "What you doing late, man? You can't be doing that up in Princeton." So I would like to thank Chris because he actually stayed on me. Okay. I would like to thank Wally, Claude, Mr. Stackhouse. I don't see Ali. He must have stepped out. Oh, okay. But I would like to thank you all. And I have a brother here from New Jersey STEP Scholarship and Transformative Educations in Prison. And Sammy has been very instrumental as far as seeing me along my way when I attend Rutgers University, and he and I communicate often about our challenges that we're faced with, and in the colleges, and making the transition from being a system impacted individual and then having to re-enter society and start all over again. And so with my research project, it raised my awareness about, what people are faced with in life, particularly low-income people of color. And so it touched my heart. This really touched me. It took me a while. I had some challenges, but it touched me because it spoke about a life that I had lived. It spoke about the times when I faced eviction and my family and my friends faced eviction. And it really opened my eyes about the federal subsidies and the benefits that homeowners receive over renters, and the causes and consequences of poverty. It just really opened my eyes, and it's something that's so important. It's really important to me, and I hope it's all important to you, because a situation like this, what goes on here, has the ability to impact your lives as well. Some people that are evicted, they turn to the streets and they don't know what to do in these urban areas. And they steal to eat. They steal to put food and clothing on themselves. And that's a crime. And some of them end up in prison, like I did. And so I hope that this is well received by all of you. And I really and truly, from the bottom of my heart, I thank you for your time. I thank you for my cohorts, colleagues, everyone here. And I thank you for Princeton University for having me, the Eviction Lab, and everyone. And I'm opening the floor to any questions. Do we have any questions? Okay, we have Chris over here. Oh, come on, Chris. I was on time today, right?
Time. You already know if you're on time, you're late already.
Okay. Okay.
So yeah, like this is very fascinating work and research, and this has been something that I've also interacted with, and I wanted to know a little bit more about accountability. So what I've seen is, we have names that call them slumlords at times, but you'll have individuals who run apartment complexes, that may let them, just basically fall into a dilapidated state. They may raise rents at their own discretion, and they'll have the backing of a court system behind them to basically do what they want to do. Is there anything being put in place to hold these individuals more accountable, and does that intersect with your research in any way?
Okay, Chris. So that is an excellent question, and yes, I can answer that question. Okay, and I'm going to say it simply in the beginning, but I'm going to elaborate a little bit. So there is a system in place, and we call that. Some people call it the criminal justice system. Some people call it the criminal legal system, but I call it a system of racial injustice. And I'll tell you, to answer your question, when someone is dealing with, so you call them a bum landlord, a slum landlord, okay. When someone is in that situation, you have what we call the criminal justice system, right? And so just as a landlord could take a tenant to court, a tenant can take a landlord to court. And that falls up under landlord-tenant law. And if you want to know more about landlord-tenant law, you can look in New Jersey statutes annotated, and it will tell you what you need to do to move forward through the courts. You would also want to consult the court rules, New Jersey court rules. So to answer your question, when a tenant is faced with issues such as bad plumbing, flooding, ceiling leaking, you name it, bad railings, then that tenant has a right to begin a process through the criminal justice system. And they would do that by filing a complaint and a summons against their landlord. They would only need the landlord's address, contact information, and that it would be how they handle it. Now, I heard you say something about raising rent. There is some laws that limit landlords from raising the rent to, I'm not sure, I think the last time I read it was about 6%, but each year a landlord cannot exceed that. And I could be incorrect with the 6%. That was the last time I read it in my researches, and that was quite some time ago. But the landlord cannot just boost up your rent and say, oh, you were paying me $1,200, and now all of a sudden you got to give me $1,300. No, the law does not permit that. So there are ranges that landlords must follow. And I hope that answers your question. Is there any other questions? Wow. Wow, dang, I guess I did good. Thank you.